Right now, somewhere in the universe, a star is dying, not quietly fading away, but preparing for the most violent explosion nature can produce, a supernova, and when it happens, that single star will briefly outshine an entire galaxy of hundreds of billions of suns. Picture this: you're standing outside on a clear night, looking up at the familiar constellations. Tomorrow night, you look up again, and there's a new star, blazing so bright it casts shadows, visible even in daylight. That's what happened in 1006 AD when a supernova appeared in the constellation Lupus. It was 16 times brighter than Venus. People could read by its light at midnight. But here's what makes this truly extraordinary. That star was 7,000 light years away. 7,000 light years. And it was still bright enough to illuminate medieval manuscripts. What kind of explosion does that? We're talking about an event so energetic that in a few seconds it releases more power than our sun will produce in its entire 10 billion year lifetime. More energy than a trillion nuclear bombs. Numbers so large they stop making sense. Yet for all their violence, supernovae aren't just cosmic fireworks. They're foundational. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in the heart of dying stars and scattered across the cosmos by supernova explosions. You are literally made of stardust. But not the gentle, romantic kind. The violent, explosive kind. So what actually happens when a star goes supernova? How does something that's been peacefully burning for millions of years suddenly tear itself apart with such fury? And why do only certain stars explode while others fade quietly into the cosmic night? The story begins not with death, but with life. With how stars work in the first place. Stars are engines of nuclear fusion. At their cores, temperatures reach 15 million degrees Celsius. Hot enough to slam hydrogen atoms together so hard, they fuse into helium, releasing tremendous energy in the process. This energy pushes outward, while gravity pulls inward. For most of a star's life, these forces balance perfectly. It's a standoff, pressure versus gravity. And as long as there's fuel to burn, the star stays stable. But here's the thing about fusion. It's picky. Hydrogen fuses into helium easily enough, but once you've built up helium, fusing it into heavier elements requires even higher temperatures and pressures. Carbon needs more energy still. Oxygen, more again. Each fusion stage burns faster than the last. A star might spend 10 million years burning hydrogen, 1 million years burning helium, 1,000 years burning carbon. Oxygen? A year. Silicon? A week. The star is racing toward a finish line it can't see. Now, you might think this process continues indefinitely. Keep fusing heavier and heavier elements forever. But physics has other plans. Because there's one element where everything stops. Iron. Iron is special. It's the most stable element in the universe. Fusing iron doesn't release energy. It absorbs energy. Iron is the end of the line, the point where fusion becomes a losing game. So imagine you're a massive star. You've spent millions of years building up layers like a cosmic onion, hydrogen burning in the outermost shell, helium burning beneath that, carbon, neon, oxygen, silicon, each layer burning at increasingly insane temperatures. And at the very center, iron, dead iron, inert, taking up space but contributing nothing. The core keeps growing. More silicon fuses into iron. The iron core gets heavier and heavier, and gravity starts to win. For stars like our sun, this isn't a problem. the Sun will never build an iron core. It'll puff up into a red giant, shed its outer layers, and settle down as a white dwarf. A slow, dignified retirement. But for stars at least 8 times more massive than the Sun, they're heading for something very different. The iron core grows until it reaches a critical threshold. About 1.4 times the mass of our Sun, compressed into a sphere roughly the size of Earth. At this point, the pressure becomes so extreme that something remarkable happens. Electrons get crushed into protons. They combine to form neutrons and release ghostly particles called neutrinos. The core, which was being supported by electron pressure, suddenly loses that support, and it collapses. Not slowly, not gradually. In less than a second, the core implodes at speeds up to 23% of the speed of light. 23%. Of light speed, the temperature skyrockets to 100 billion degrees. That's hotter than any temperature anywhere else in the universe, except during the Big Bang itself. The entire core, containing more mass than our Sun, collapses to a sphere just 30 kilometers across. 30 kilometers from something the size of Earth. The collapse happens so fast that the outer layers of the star don't even know it's happening yet. They're still falling inward, expecting the core to be there to catch them. But the core isn't there anymore. It's compressed into something else entirely. A ball of neutrons so dense that a teaspoon would weigh 1 billion tons. A neutron star. Or if the star was massive enough, something even stranger. A black hole. Now here's where it gets violent. The infalling outer layers slam into this impossibly dense core and bounce, like a rubber ball hitting concrete. Except this ball is made of stellar material moving at a significant fraction of light speed, and the concrete is a neutron star. The bounce creates a shockwave, a wall of pressure and energy that races back outward through the star at 10,000 kilometers per second. Everything in its path gets obliterated and accelerated to escape velocity. The star doesn't just explode, it detonates. Within hours, the shockwave punches through the star's surface in what astronomers call the shock breakout. This is the moment when the supernova becomes visible. A flash of X-rays and ultraviolet light announces to the universe that another star has died. But most of the energy doesn't go into light. It goes into neutrinos. Remember those ghostly particles released when electrons merged with protons? In 10 seconds, the collapsing core releases 10 to the power of 58 neutrinos. That number is so large it's almost meaningless. More neutrinos than there are stars in 1 million galaxies. These neutrinos carry away 99% of the explosion's energy. They pass through matter like it isn't even there. Trillions of them are passing through your body right now from distant supernova, and you don't feel a thing. But in 1987, we caught them. Supernova, 1987. A exploded in the Large Magellanic Cloud, a small galaxy near our own. It was the closest supernova visible to the naked eye in 400 years. And about 3 hours before the light reached Earth, neutrino detectors in Japan and Ohio registered 25 neutrinos arriving within 13 seconds. 25 out of 10 to the 58. That's like standing in a rainstorm and catching 25 specific raindrops. But those 25 neutrinos told us something profound. The theoretical models were right. Core collapse really does produce a massive neutrino burst. We'd caught the star in the act of dying. And because neutrinos travel at nearly light speed and pass through matter easily, they escaped the star hours before the light did. The light had to fight its way through thousands of kilometers of stellar material. The neutrinos just left. For the first time, we detected a supernova in neutrinos before we saw it in light. The shockwave, meanwhile, is doing something extraordinary. As it tears through the star's outer layers, it's compressing and heating material to such extreme temperatures that new nuclear reactions ignite. Not fusion to release energy, fusion to create elements. Remember how iron was the end of the line for normal fusion? Well, in a supernova, all bets are off. The conditions are so extreme that elements heavier than iron can form. Cobalt, nickel, copper, zinc, keep going, silver, tin, gold, platinum, lead, uranium. Every atom of gold in every ring, every coin, every circuit board was created in a supernova explosion. The extreme pressures and temperatures in that expanding shockwave are the only natural forge capable of building these heavy elements. A single supernova can produce more gold than exists in Earth's entire crust. The shockwave expands outward at 5 to 20,000 kilometers per second, roughly 6% of light speed. It's carrying with it all the elements the star spent millions of years creating: oxygen, carbon, silicon, iron, and all those heavy elements born in the explosion itself. This material slams into the surrounding interstellar gas, heating it, compressing it, mixing with it. Over thousands of years, the expanding debris will slow down and cool off, forming what we call a supernova remnant, a beautiful, glowing shell of gas expanding through space. The Crab Nebula is one such remnant. It's what's left of the supernova observed by Chinese astronomers in 1054 AD. That explosion was visible in daylight for 23 days and remained visible at night for 653 days, nearly 2 years. Today, the Crab Nebula spans 11 light years and is still expanding. At its center sits a neutron star, spinning 30 times per second, the crushed core of the star that exploded. But not all supernovae are created equal. What I've just described is a core collapse supernova, also called a Type II supernova. These require massive stars, at least 8 times the mass of our Sun, sometimes up to 200 solar masses. There's another kind, Type 1a, and it's stranger. Type 1. A supernovae don't come from massive stars at all. They come from white dwarfs, the dense remnants of stars like our Sun that have already died once. Here's how it works. A white dwarf sits in a binary system with another star. Maybe a red giant, maybe another white dwarf. And material from the companion star falls onto the white dwarf's surface. Slowly, over thousands or millions of years, the white dwarf gets heavier and heavier until it approaches a critical mass, 1.44 times the mass of the Sun. This is called the Chandrasekhar limit, and it's a hard boundary. Below this mass, electron degeneracy pressure can support the white dwarf against gravity. Above it, the pressure fails. The carbon and oxygen in the white dwarf's core reach ignition temperature, and the entire star detonates in a runaway fusion reaction. Unlike core collapse supernovae, which leave behind a neutron star or black hole, Type 1a supernovae destroy their stars completely. Nothing remains but an expanding cloud of debris. These explosions are remarkably consistent. They all reach roughly the same peak brightness because they all happen at the same mass threshold. This makes them incredibly useful as cosmic distance markers. If you know how bright something actually is and you measure how bright it appears, you can calculate how far away it is. Type 1. A supernovae are one of the main tools we use to measure the expansion rate of the universe. In fact, It was observations of distant Type 1a supernovae that led to the discovery of dark energy in 1998. But whether we're talking about core collapse or thermonuclear explosion, the result is similar. A star that was stable for millions of years suddenly releases more energy than seems physically possible. The numbers are staggering. A typical supernova releases about 10 to the 44th joules of energy. That's a 1 followed by 44 zeros. In watts, the power output peaks at 10 to the 45 or 46 watts. For comparison, our sun outputs about 4 times 10 to the 26 watts. A supernova, for a brief time, can be 5 trillion times more luminous than the sun, 5 trillion times brighter than the object that lights our entire world. And here's something that might blow your mind. On April 10th, 2024, astronomers detected a supernova designated SN2024GGI. Just 26 hours later, they pointed the Very Large Telescope at it. 26 hours. That's barely more than a day. What they saw was unprecedented. They caught the shock breakout, the actual moment when the shockwave punches through the star's surface. This phase lasts only a few hours, and catching it requires being incredibly lucky or incredibly fast. The observations revealed something unexpected. The initial blast wasn't spherical. It was shaped like an olive, elongated, asymmetric. This tells us something profound about how stars explode. The physics isn't as simple as a uniform shockwave expanding in all directions. There are instabilities, asymmetries. The star's rotation, magnetic fields, and internal structure all affect how it tears itself apart. Every supernova is unique, a fingerprint of the star that died. But here's what connects all of this. From the crushing collapse of an iron core to the runaway fusion of a white dwarf, from the olive-shaped blast of SN2024GGI to the perfectly spherical expansion of other explosions, it's all driven by the same fundamental forces. Gravity trying to crush everything into a point, pressure pushing back, and nuclear physics determining what happens when you compress matter beyond all reasonable limits. The question is, what happens next? After the shockwave passes, after the light fades, after the neutrinos have scattered across the cosmos, what's left behind? And how does that remnant continue to shape the universe around it? The expanding debris field becomes a cosmic laboratory. Temperatures in the billions of degrees. Pressures that make the center of our sun look like a gentle breeze. And in these extreme conditions, something remarkable happens. Elements that could never form in a normal star suddenly come into existence. Iron was the ceiling for normal fusion, the end of the line. But in a supernova's shockwave, that ceiling shatters. The shock compresses material so violently that nuclei slam together with enough force to overcome the energy barrier. They fuse into heavier elements: cobalt, nickel, copper, zinc, all the way up to uranium and beyond. This is shockwave nucleosynthesis, and it's the only place in the universe where many elements can form. The gold in jewelry, the silver in electronics, the uranium in nuclear reactors. None of these existed in the early universe. They weren't created in the Big Bang. They couldn't form in stellar cores. They required the violence of a supernova to be forged. Think about that for a moment. Every atom of gold on Earth was created in a stellar explosion. Every platinum ring, every gold bar in a vault somewhere. All of it came from a star that died before our sun was born. These atoms were scattered into space, mixed with hydrogen and helium, and eventually condensed into the cloud that became our solar system. You're made of stardust. That phrase gets thrown around a lot, but it's literally true. The calcium in your bones was created in a supernova. The iron in your blood was forged in the final moments of a dying star. The oxygen you're breathing right now was synthesized in stellar cores and scattered by supernova. Every breath you take contains atoms that were once inside a star, but the explosion doesn't create elements uniformly. Different regions of the expanding debris have different compositions. The innermost layers, closest to where the core collapsed, are rich in iron group elements: iron, nickel, cobalt. These were the last elements the star created before it died. Moving outward, you find lighter elements: silicon, sulfur, oxygen. These came from earlier stages of the star's life. The outer layers contain helium and hydrogen, barely processed by nuclear reactions. The debris field is stratified, layered like an onion, with each shell telling a story about a different phase of the star's evolution. As this material expands, it collides with the surrounding interstellar medium, the gas and dust floating between stars. This collision creates a shock front, not the initial shockwave from the explosion, but a boundary where the fast-moving debris slams into slower-moving gas. This collision heats the gas to millions of degrees. It glows in X-rays, and it creates what we call a supernova remnant. The Crab Nebula is one of the most famous examples, created by the supernova of 1054 AD. Chinese astronomers saw it appear, a new star bright enough to see in daylight for 23 days, visible at night for 653 days. Nearly 2 years of watching a star that shouldn't exist slowly fade from view. Today, almost 1,000 years later, the debris is still expanding, still glowing, still visible through telescopes as a complex filamentary structure. Gases moving at thousands of kilometers per second, magnetic fields twisted into intricate patterns, and at the center, something we haven't discussed yet. Something that survived the explosion. A neutron star, the collapsed core of the original star, only about 20 kilometers across, less than the width of a city, but containing more mass than our sun. It spins 30 times per second. Each rotation sweeps a beam of radiation across space like a cosmic lighthouse. We see these beams as pulses, regular, precise. So precise we initially thought they might be signals from alien civilizations. The Crab pulsar was one of the first discovered, proof that neutron stars weren't just theoretical objects. They were real, dense beyond comprehension. A teaspoon of neutron star material would weigh 1 billion tons on Earth. Gravity so strong that if you dropped something from a height of 1 meter, it would hit the surface at millions of kilometers per hour. But not all supernovae leave neutron stars behind. If the original star was massive enough, the core collapse doesn't stop at neutron degeneracy. It keeps going, crushing neutrons themselves, overcoming every force physics can muster, and creating a black hole. The transition point is somewhere around 20 to 25 solar masses. Stars below that limit create neutron stars. Stars above it create black holes. But the exact boundary is fuzzy. It depends on the star's composition, its rotation rate, how much mass it shed during its lifetime. Every star is different. Cassiopeia A is another famous remnant, created by a supernova that should have been visible from Earth around 1680, but nobody recorded seeing it. Perhaps it was obscured by dust, Perhaps it happened during cloudy weather, or perhaps the explosion was unusually faint. We'll never know for certain. What we do know is that the remnant is extraordinary. The fastest moving debris we've ever measured in a supernova. Filaments of gas racing outward at 13.4 million miles per hour, about 2% of light speed, carrying kinetic energy that staggers the imagination. The shockwave from Cassiopeia A is still expanding today, still sweeping up interstellar gas, still heating it to millions of degrees. And in the process, it's creating cosmic rays, high-energy particles accelerated to nearly light speed by the magnetic fields in the shock front. These cosmic rays are everywhere. Right now, thousands of them are passing through your body every second. Most of them created in supernova remnants scattered across the galaxy. They're one reason we know supernovae are important beyond just making heavy elements. They're cosmic particle accelerators, nature's own version of the Large Hadron Collider, but vastly more powerful. The energy in a supernova remnant doesn't disappear quickly. It takes tens of thousands of years for the debris to slow down, to merge with the interstellar medium, to cool and fade from view. During that time, the remnant goes through stages. First, free expansion. The debris moves outward at constant velocity, barely interacting with surrounding gas because there's so little of it. This phase lasts anywhere from decades to a few centuries, depending on how dense the local environment is. Then the Sedov-Taylor phase begins. The remnant has swept up enough interstellar gas that it starts to matter. The expansion slows. The shock front strengthens. The remnant becomes a bubble of hot, glowing gas pushing into the cooler material around it. This phase can last thousands of years. Eventually, the remnant cools enough that it stops glowing in X-rays. It becomes just another cloud of gas in the interstellar medium, slightly enriched in heavy elements compared to its surroundings, slightly denser, and potentially a trigger for new star formation. Because when a supernova remnant plows into a molecular cloud, it compresses the gas, squeezes it. And compressed gas is unstable. Regions that are slightly denser than average begin to collapse under their own gravity. They fragment into smaller clumps, and those clumps become the seeds of new stars. This is how star formation propagates through a galaxy. One generation of stars lives and dies. Their supernovae trigger the formation of the next generation. It's a cycle that's been running for billions of years. The reason our galaxy is full of stars of different ages. The reason new stars are still forming today. Our own sun might have been triggered by a supernova. There's evidence in meteorites. Specifically, in their composition, they contain isotopes of elements that decay quickly. So quickly they shouldn't still be around unless they were created shortly before the solar system formed. The most likely source? A nearby supernova that enriched the cloud of gas that became our solar system and possibly triggered its collapse. If that's true, we owe our existence to a star that died 4.6 billion years ago. A star we'll never know the name of, never see, but whose final explosion set in motion the chain of events that led to planets, to Earth, to life, to you reading these words right now. But supernova remnants do more than trigger star formation. They heat the interstellar medium, keep it from collapsing too quickly, too completely. Without supernovae, galaxies would be very different places. Gas would cool, condense, form stars far more rapidly than it does. The star formation rate would be higher, but the stars would be smaller on average, less massive. It's a balance. Supernovae inject energy into the galaxy, heat things up, stir the pot. This prevents runaway star formation, regulates the process, ensures that galaxies like ours form stars steadily over billions of years, rather than burning through all their gas in a single burst. The debris from a supernova also enriches the interstellar medium. Before the first supernova, the universe contained only hydrogen, helium, and trace amounts of lithium. Everything else had to be created in stars and distributed by explosions. Generation after generation of stars lived and died, each one adding more heavy elements to the cosmic mix. The first stars were massive, hundreds of times the sun's mass. They lived fast and died young. Their supernovae scattered the first heavy elements into space. The next generation of stars formed from gas slightly enriched in carbon and oxygen. Those stars lived and died, added more elements, and so the cycle continued. Our sun is a third or fourth generation star, maybe later. It formed from gas already enriched in heavy elements. That's why Earth exists, why rocky planets could form, why we have the elements necessary for complex chemistry, for life. Every supernova adds to this enrichment, mixes new elements into the galactic gene pool, and slowly, over billions of years, the composition of the galaxy changes. The first galaxies were pure hydrogen and helium. Modern galaxies have a few percent heavy elements. In another few billion years, that percentage will be higher still. There's another way to think about this. Every element heavier than helium in your body was created in a star. Most of those elements were scattered by supernovae. You are quite literally made from the ashes of dead stars. Recycled stellar material. Atoms that have been through multiple generations of stars, multiple cycles of birth and death, the oxygen in water, the carbon in proteins, the nitrogen in DNA, the calcium in bones, the phosphorus in ATP, the iron in hemoglobin. All of it was forged in stellar cores or supernova shockwaves. All of it was scattered into space by dying stars. All of it eventually found its way into the cloud that formed our solar system. Supernovae are more than just explosions. They're the mechanism by which stars give back to the universe, how they enrich the cosmos, how they make future generations of stars and planets possible. Without supernovae, the universe would be a much simpler place. No rocky planets, no complex chemistry, no life. But there's something else supernovae create. Something we haven't fully explored yet. When that core collapses, when it reaches densities beyond anything found in normal matter, what exactly is left behind? What is a neutron star really? And what happens in the most extreme cases when even neutron stars can't form? That's the question we need to answer. What happens when gravity wins so completely that even atoms can't survive? The remnant left behind depends on the mass of the original core. If the core is between about 1.4 and 3 solar masses, you get a neutron star. Above that threshold, something even stranger emerges. But let's focus on neutron stars first, because they're already bizarre enough. Picture compressing Mount Everest into a teaspoon. That's the density we're talking about. A neutron star is matter crushed so tightly that protons and electrons merge into neutrons. The entire star becomes one giant atomic nucleus, roughly 20 kilometers across, containing more mass than the sun. The physics at these densities is extreme. Gravity is so strong that it warps space-time noticeably. Light bends around the star. Time runs slower near the surface. And the magnetic fields, those are in a category of their own. Some neutron stars have magnetic fields trillions of times stronger than anything we can create on Earth. These are called magnetars. Their magnetic fields are so intense they could kill you from 1,000 kilometers away. Not through radiation, through the magnetic field itself, distorting the electron clouds in your atoms. Neutron stars rotate fast. Some spin hundreds of times per second. This isn't random, it's conservation of angular momentum. The core that collapsed was already rotating. As it shrinks, it spins faster. Same principle as a figure skater pulling in their arms, except instead of a human spinning faster, you have a stellar core rotating at a significant fraction of light speed at its equator. Some neutron stars emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like cosmic lighthouses. When one of these beams points toward Earth, we detect regular pulses of radiation. We call these objects pulsars. They were discovered in 1967 by Jocelyn Bell Burnell. At first, the signals were so regular they were nicknamed LGM1, Little Green Men. Seriously, the pulses were that precise. Turns out it wasn't aliens, just physics being weird. The material inside a neutron star exists in states we can barely describe. Near the surface, you have a crystalline crust, iron nuclei packed into a rigid lattice. Deeper down, neutrons start to drip out of nuclei. Deeper still, you reach a neutron superfluid, frictionless, flowing without resistance. And at the very center, we don't actually know. The pressure there exceeds anything we can recreate in laboratories. Matter might break down into quarks, or form exotic states we haven't even theorized yet. Here's something that'll bend your mind. Despite being incredibly dense, neutron stars aren't black holes. Light can still escape. You could theoretically stand on the surface. Well, not really. You'd be crushed instantly and vaporized by radiation. But in principle, there's a surface, a place where matter exists, unlike what's coming next. Because if the core is too massive, even neutron degeneracy pressure can't hold it up. Above roughly 3 solar masses, there's no known force that can stop the collapse. The core doesn't stop shrinking. It doesn't bounce. It just keeps falling inward, past the point where neutrons touch, past the point where matter has any meaning, until it becomes something we can barely comprehend. A black hole. The term is misleading. Black holes aren't holes, they're objects, extremely dense objects, but they're hidden behind an event horizon, a boundary in space-time beyond which nothing can escape. Not matter, not light, not information. Once you cross that threshold, all paths lead inward. There's no going back. It's not a physical barrier. It's a geometric inevitability. The curvature of space-time becomes so extreme that returning would require moving faster than light. What happens to the collapsing core? Nobody knows. General relativity predicts it forms a singularity, a point of infinite density. But infinite densities are probably unphysical. Our equations break down. We need quantum gravity to describe what really happens. And we don't have that theory yet. So the honest answer is, we don't know what's at the center of a black hole. We know what's outside. We can describe the event horizon, the ergosphere, the photon sphere. But the core itself, that's still a mystery. Not all black holes form from supernovae. Some form when neutron stars collide. Others grow by accreting matter over time. The black holes at the centers of galaxies probably form through mergers. Countless smaller black holes combining over billions of years. Our galaxy has one, Sagittarius A star, 4 million solar masses, sitting quietly at the galactic center, occasionally eating a star that wanders too close. But stellar mass black holes, those formed from supernovae, range from about 3 to 100 solar masses, maybe more. We've detected some through gravitational waves. When two black holes orbit each other, they lose energy. The orbit decays. Eventually they merge, and when they do, they release gravitational waves, ripples in space-time itself. LIGO detected the first one in 2015. Two black holes, each about 30 solar masses, spiraling together. The collision released more energy than all the stars in the observable universe combined, for a fraction of a second. That's gravitational wave astronomy, a completely new way of observing the universe. We're not using light anymore. We're detecting distortions in the fabric of space-time, ripples from the most violent events in the cosmos. Black hole mergers, neutron-star collisions, maybe even echoes from the Big Bang itself. It's like gaining a new sense. We spent our entire history looking at the universe through light. Now we can feel it too. Neutron-star collisions are particularly interesting. When two neutron stars merge, they create what's called a kilonova. It's similar to a supernova but powered by different physics. The collision ejects neutron-rich material at high speeds. That material undergoes rapid neutron capture, the Are process. Elements heavier than iron form: gold, platinum, uranium, all the really heavy elements in the periodic table. Most of them come from kilonovae. In 2017, we detected gravitational waves from a neutron star merger, GW170817. But we also saw it in light, gamma rays, X-rays, visible light, infrared, radio waves. Every telescope on Earth and in space turned to look. It was the most studied astronomical event in history, and it confirmed something we'd suspected. Kilonovae are the primary source of heavy elements in the universe, the gold in jewelry, the uranium in nuclear reactors. All of it was forged in neutron star collisions, scattered across space, mixed into the clouds that formed later stars and planets. You're wearing atoms from dead neutron stars. The calcium in your bones might have come from a supernova. But the iodine in your thyroid, that probably came from a kilonova. Two neutron stars colliding billions of years ago, creating the elements necessary for complex chemistry, for biology, for you. This brings us back to supernovae, because they're not just explosions, they're part of a cycle. Stars form from gas clouds. They fuse lighter elements into heavier ones. They explode. They scatter enriched material back into space. New stars form from that enriched material, and the cycle continues. Each generation of stars is slightly richer in heavy elements than the last. The first stars in the universe contained almost no heavy elements, just hydrogen and helium from the Big Bang. They were massive, hundreds of solar masses. They lived fast, died young. Their supernovae scattered the first carbon and oxygen into space. The next generation of stars formed from slightly enriched gas. Those stars added more elements. And so it went, generation after generation. The universe slowly filling with the debris of dead stars. Our Sun is a late generation star. It formed about 4.6 billion years ago from a cloud already rich in heavy elements. That's why we have rocky planets. Why Earth exists. The first generation of stars couldn't have planets like Earth. There wasn't enough solid material, just gas. But by the time our solar system formed, there was plenty of carbon, oxygen, silicon, iron, enough to build planets, moons, asteroids, and eventually, life. Supernovae made that possible. Without them, the universe would be a simpler place. Hydrogen and helium, gas clouds, maybe some stars, but no complexity, no chemistry, no life. Every element in your body heavier than helium was created in a star. Most of those elements were scattered by supernovae. You exist because stars die violently. There's something poetic about that. Stars live for millions or billions of years, quietly fusing hydrogen into helium, then helium into carbon, carbon into oxygen, building up layers, creating heavier and heavier elements until they reach iron, the end of the line, and then they die, collapse, explode, and give everything back to the universe. The energy output is staggering. A typical core collapse supernova releases about 10 to the 44th joules of visible light. That's more energy than the sun will emit in its entire 10 billion year lifetime, released in a few weeks. But that's not even the main energy output. The neutrinos carry away far more, about 10 to the 46th joules. 99% of the explosion's energy leaves as neutrinos, weakly interacting particles that pass through the expanding debris, almost unhindered. They stream out at nearly light speed, carrying information about the core collapse. In 1987, we detected neutrinos from a supernova for the first time. SN 1987A. It exploded in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way, about 160,000 light-years away. 2 neutrino detectors on Earth picked up the signal, about 20 neutrinos total, out of the 10 to the 58 that the supernova released. That's how weakly neutrinos interact. 58 orders of magnitude were created, 20 detected. But those 20 confirmed our models. Told us we understood core collapse, at least roughly. The detection happened hours before the light arrived. Because neutrinos escaped immediately, light had to diffuse through the expanding debris. It took time, hours or days. The neutrinos got a head start. This will be important for future supernova observations. If we detect a neutrino burst from a nearby supernova, we'll know to point our telescopes at that part of the sky before the light arrives, before the shock breaks through the surface. We might catch the shock breakout, that brief flash when the shock wave first emerges. It's one of the brightest phases, but it only lasts a few hours. Shock breakout is hard to observe. You need to be looking at the right star at exactly the right time. Most supernovae are discovered after they've already brightened. We miss the early phases, but in 2024, astronomers got lucky. SN 2024. GI was caught just 26 hours after the explosion. They pointed a telescope at it immediately, caught the shock breakout, saw the initial flash, and learned something surprising. The shockwave wasn't spherical, it was shaped like an olive, stretched along one axis, compressed along another. This tells us something about the star before it exploded. Red supergiants aren't perfect spheres. They're lumpy, turbulent. Convection currents churn through their outer layers. The shockwave follows the path of least resistance, where the density is lower, so it breaks out asymmetrically, in this case, in an olive shape. That's new information. Our models assumed spherical explosions. Reality is messier, and that's the theme here. Reality is always more complicated than our models suggest. Supernovae aren't clean. They're chaotic, asymmetric, turbulent. The core doesn't collapse smoothly. It wobbles, sloshes, the shockwave stalls. Neutrinos might help revive it. Magnetic fields twist, rotation matters. Every supernova is unique. Different mass, different composition, different rotation rate, different magnetic field. The details matter, and we're still learning what those details are. But here's where it gets even stranger. Not all supernovae follow the same path. We've been talking about core collapse, massive stars running out of fuel, iron cores imploding, shockwaves blasting outward. That's type 2, and types 1b and 1c, which are similar but have lost their outer hydrogen layers before exploding, stripped by stellar winds or companion stars. But there's another category entirely. Type 1a. These don't come from massive stars at all. They come from white dwarfs. White dwarfs are stellar corpses, the remnants of stars like our Sun, stars that weren't massive enough to go supernova themselves. They burned through their fuel, hydrogen to helium, helium to carbon and oxygen, then stopped. No more fusion. The core contracted, became incredibly dense, a star's worth of mass compressed into something the size of Earth, held up not by thermal pressure, but by quantum mechanics. Electron degeneracy pressure, electrons packed so tightly they can't be squeezed any closer. This pressure supports the white dwarf against gravity, but there's a limit, the Chandrasekhar limit, about 1.44 solar masses. If a white dwarf exceeds this mass, electron degeneracy pressure fails, gravity wins, the star collapses, and something remarkable happens. Most white dwarfs sit quietly, cooling slowly over billions of years. But some exist in binary systems, two stars orbiting each other. If the companion is a normal star close enough, the white dwarf can steal material, accrete it, pull gas from the companion's outer layers onto itself. Slowly, over millions of years, the white dwarf gains mass, approaches the Chandrasekhar limit, or sometimes two white dwarfs orbit each other, losing energy to gravitational waves, spiraling inward. Eventually they merge, combine their masses, exceed the limit. Either way, once you cross 1.44 solar masses, the white dwarf becomes unstable. It starts to collapse. And here's the critical difference from core collapse supernovae. White dwarfs are made of carbon and oxygen, not iron. Carbon and oxygen can fuse, release energy. When the white dwarf collapses, the core heats up, reaches the ignition temperature for carbon fusion, and then everything happens at once. Carbon fusion begins, releases energy, heats the surrounding material, which triggers more fusion. Runaway reaction. The entire white dwarf becomes a nuclear bomb. No gradual burning, no layers of different elements, just instant detonation. The whole star fuses in seconds, converts to iron group elements, nickel 56 mostly, releases enormous energy, about 10 to the 44th joules, similar to core collapse, but the mechanism is completely different. The white dwarf is completely destroyed, nothing left behind, no neutron star, no black hole, just expanding debris, moving at 10,000 kilometers per second, 6% light speed, slightly slower than core collapse ejecta, but still incredibly fast. Type 1. A supernovae are important for cosmology because they're remarkably consistent. Every type 1a has roughly the same peak brightness, about 5 billion times brighter than the Sun. This makes them standard candles. If you know how bright something is intrinsically, and you measure how bright it appears, you can calculate its distance. Simple inverse square law. A Astronomers use Type 1a supernovae to measure distances across the universe, billions of light years, far beyond where other methods work. This is how we discovered dark energy. In the late 1990s, two teams studied distant Type 1a supernovae, expected to see the universe's expansion slowing down, gravity pulling everything back together. But they found the opposite. The expansion was accelerating. Distant supernovae were dimmer than expected, farther away than they should be. Something was pushing the universe apart. We call it dark energy. Still don't understand what it is. But Type 1a supernovae revealed its existence. Though even Type 1a aren't perfectly uniform, there's scatter. Some are brighter, some dimmer. Astronomers have learned to correct for this, standardize them, use the light curve shape, how quickly they brighten and fade. Brighter ones fade slower, dimmer ones fade faster. There's a relationship. You can measure the light curve, apply corrections, get a more accurate standard candle. And recently we've found exceptions. Superchandrasekhar supernovae, Type 1a events that seem to come from white dwarfs exceeding 1.44 solar masses, some up to 2.4 solar masses. How? We're not sure. Maybe rapid rotation, centrifugal force providing extra support, or strong magnetic fields. Adding pressure, these are rare, but they exist, and they challenge our models. What happens after a supernova? The star is gone, destroyed, but it leaves something behind, a remnant. For Type 1a, it's just expanding debris, gas and dust spreading into space. But for core collapse, there's also the core, the collapsed remnant. If the original star was between about 8 and 20 solar masses, the core becomes a neutron star, something extraordinary. The core collapses until neutrons themselves provide degeneracy pressure, similar to electron degeneracy in white dwarfs, but at even higher density. A neutron star contains about 1.4 solar masses, compressed into a sphere 20 kilometers across, a city-sized ball of neutrons, density beyond comprehension. A teaspoon of neutron star material would weigh 1 billion tons on Earth. Neutron stars are laboratories for extreme physics. Gravity so strong it warps space-time noticeably. Magnetic fields 1 trillion times Earth's. Some neutron stars spin hundreds of times per second. Pulsars. We detect them as rhythmic pulses of radio waves. Lighthouse beams sweeping across space, incredibly precise. Some pulsars keep time better than atomic clocks, but if the core is massive enough, even neutron degeneracy can't hold it up. Above about 3 solar masses, nothing can stop the collapse. The core shrinks to 0 volume, infinite density, a singularity, surrounded by an event horizon. A black hole forms, the ultimate endpoint, where matter disappears from the observable universe, falls into a region where even light can't escape. We think most massive stars, above about 20 solar masses, leave black holes. Smaller ones leave neutron stars. The boundary isn't sharp. Depends on mass loss during the star's life. How much material was blown away by winds, whether it had a companion stripping mass. The final core mass determines the remnant. Either way, the explosion itself creates a supernova remnant, the expanding debris from the star's outer layers. This material plows into the surrounding interstellar medium, sweeps it up, creates a shock wave. The remnant grows, hundreds of light years across eventually, glowing in X-rays and visible light. We can see many of them in our galaxy. The Crab Nebula is a famous example. Remnant of SN 1054, The supernova Chinese astronomers recorded in July 1054. It appeared in the constellation Taurus, bright enough to see during the day, visible for 23 days in daylight, 653 days at night, then faded, but it left behind a glowing cloud. Still expanding today, still visible through telescopes. At its center, a pulsar, spinning 30 times per second. The collapsed core. Cassiopeia A is another, younger. Exploded about 340 years ago, but we don't have historical records. It should have been visible, bright enough, but no one recorded it. Maybe obscured by dust, or maybe we just missed it. Happens. The remnant is spectacular, one of the brightest radio sources in the sky, expanding at 13 million miles per hour. Fastest supernova shock wave we know. These remnants are crucial. They're where the heavy elements mix into space. Carbon, oxygen, silicon, iron, all forged in the star's core, blasted outward by the explosion. Eventually, this material will be incorporated into new stars, new planets. Us. Every atom in your body heavier than helium came from a star, most from supernovae. You're made of stardust, literally. Supernova remnants also accelerate cosmic rays, high-energy particles that zip through space at nearly light speed. Protons mostly, some heavier nuclei. They bombard Earth constantly. We're not sure exactly how supernovae accelerate them. Something to do with the shock waves, magnetic fields, particles bouncing back and forth across the shock, gaining energy each time, eventually reaching enormous energies. Some cosmic rays have energies equivalent to a baseball traveling 60 miles per hour, concentrated in a single proton. We don't know how that's possible, but supernovae are the leading candidates. The remnants can also trigger new star formation. If the expanding shockwave encounters a molecular cloud, it compresses the gas. Density increases. Gravity takes over. Regions collapse. Form new stars. So supernovae seed their own replacements. One generation dying, enriching the galaxy, triggering the next generation. Our sun might have formed this way. There's evidence. Meteorites contain isotopes that decay quickly. Aluminum-26, iron-60. They shouldn't still exist. They should have decayed billions of years ago, unless they were created recently, just before the solar system formed. Supernovae produce these isotopes. The theory is a nearby supernova exploded. Shockwave hit a molecular cloud, compressed it, triggered collapse, and injected freshly made isotopes. The sun and planets formed from that enriched material. We're here because of a supernova, possibly. How often do supernovae happen? In our galaxy, about one every 50 years on average. But they're not evenly distributed. Sometimes centuries pass, sometimes multiple in a decade. And most are hidden. Our galaxy is dusty, especially toward the center. Dust blocks visible light. We can't see most of the galaxy optically. We rely on radio and infrared, X-rays, wavelengths that penetrate dust. The last visible supernova in the Milky Way was 1604, Kepler's supernova. Before telescopes existed, Johannes Kepler observed it, recorded its brightness, position. It faded after a year. Since then, nothing. 420 years. We're overdue, statistically, though that doesn't mean one is imminent. Random processes don't work that way, but we have seen supernovae in nearby galaxies. Thousands, tens of thousands. Automated surveys scan the sky nightly, looking for new points of light. Transients. Most are supernovae. We discover hundreds every year now. Study their spectra, light curves, learn about different types, progenitors, mechanisms. And we've learned something surprising. There's more variety than we thought. Superluminous supernovae, 100 times brighter than normal. We're not sure what causes them. Maybe pair instability. In very massive stars, gamma rays become so energetic they create electron-positron pairs, reduces pressure, core collapses, triggers massive thermonuclear explosion, completely destroys the star, no remnant, or maybe magnetars, neutron stars with extreme magnetic fields, spinning rapidly, releasing energy, powering the light, supernova imposters, stars that brighten like supernova, then fade, then do it again. Eta Carinae is the most famous. It erupted in the 1840s, became one of the brightest stars in the sky, then faded, but didn't explode. Still there, still massive. About 100 solar masses, probably unstable, might actually explode someday, or might not. We're watching. Calcium-rich transients, faint supernovae, rich in calcium, found far from galaxies. In intergalactic space, we don't understand them, white dwarfs maybe, but the locations are strange. The more we observe, the more complexity we find. Supernovae aren't one phenomenon. They're a family, different mechanisms, different progenitors, different outcomes. The universe is creative, finds many ways to explode stars, and we're still cataloging them, still trying to understand. Let's talk about SN 1987, A, February 23rd, 1987. Ian Shelton, astronomer, working at Las Campanas Observatory in Chile, photographing the Large Magellanic Cloud, small satellite galaxy, orbits the Milky Way, about 160,000 light-years away. He developed the photographic plate, noticed something, a bright spot. Wasn't there before, checked previous images, definitely new. He stepped outside, looked up, saw it with his naked eye. A supernova, visible without a telescope. First one since 1604. The news spread fast. Telescopes worldwide turned toward it. Observatories scrambled. Everyone wanted data. This was unprecedented. A nearby supernova. In the modern era, with modern instruments, spectroscopes, CCD cameras, radio telescopes, neutrino detectors, we could study it properly. Not just sketch its position, actually measure, analyze, understand. And it delivered. SN 1987. A taught us more about supernovae than any observation before it, maybe since 2. Here's what made it special. The progenitor star was identified, Sanjalik -69 degrees 202, a blue supergiant, about 20 solar masses. We had images of it, from before the explosion. We knew what it was. This was new. Usually we arrive after, star already gone, debris expanding. But here we had before and after. We could compare, confirm theories. The light curve was strange. It brightened, then plateaued, then brightened again. Not the smooth rise and fall we expected. Turns out the star had a complex history. It was born as a blue supergiant, then evolved into a red supergiant, expanded, then contracted back, became blue again, just before it exploded. The extended envelope, from its red phase, was still there, surrounding the core. When the shock wave hit this envelope, it created the unusual light curve, multiple peaks. We learned something. Stellar evolution isn't smooth. Stars change, contract, expand, interact with their own past. And then there were the neutrinos. 3 detectors caught them. Kamiokande in Japan, IMB in the United States, Baksan in Russia, water-based detectors. designed to catch rare interactions, neutrinos passing through, colliding with protons, creating flashes of light. On February 23rd, they all registered a burst, 12 neutrinos at Kamiokande, 8 at IMB, 5 at Baksan, within 13 seconds, from the same direction. Large Magellanic Cloud, 3 hours before the optical light arrived. This confirmed theory. Neutrinos escape first. They're weakly interacting. Pass through the star. Light takes longer. Trapped in the dense material. Scattering. Diffusing outward. Eventually breaks free. But hours later. The neutrino detection was monumental. It proved core collapse releases most energy as neutrinos, about 10 to the 53 ergs, almost all carried by neutrinos. Only 1% becomes light. Kinetic energy, the visible explosion. The rest, invisible, ghosting through the universe. We also learned about neutrino physics. The burst arrived over 13 seconds, not instantaneously. This told us something. Neutrinos have mass, very small, but not zero. Massless particles travel at light speed, all arrive together. But if they have mass, slightly slower, different energies, different speeds, small delays, measurable over 160,000 light years. From those 13 seconds, we calculated neutrino mass, less than a few electron volts, tiny, but not nothing. 1 supernova, 3 neutrino detectors, a new field born, neutrino astronomy. Now we watch for them. Always. Detectors running, waiting for the next one, because neutrinos arrive first. Early warning system. If we detect a burst, we know. Supernova happening, somewhere. Point telescopes, fast. Catch the shock breakout, the earliest light. SN 1987A also revealed rings, not immediately, took months. As debris expanded, it illuminated surrounding material, gas, dust, ejected by the star thousands of years earlier. During its red giant phase, stellar wind, blown outward, formed a structure, an hourglass, 2 lobes, connected by a ring, equatorial. The supernova lit it up like a cosmic flashlight, ultraviolet radiation, ionizing the gas, making it glow. We watched the ring brighten over years, decades. It's still visible, still evolving. The shockwave reached the ring around 2000, 13 years after the explosion. Impact, compression, heating, new emission, X-rays. The ring started changing, brightening, developing hotspots, knots, dense clumps, getting hit, radiating. We're still observing it. Hubble, Chandra, ALMA, watching the interaction. How shockwaves heat gas, transfer energy. It's a laboratory, real-time astrophysics, unfolding over decades. And we're learning about circumstellar material, mass loss, stellar winds, how stars shed mass before they die. SN 1987. A also had a mystery. The compact object. Core collapse should leave something. Neutron star or black hole. We've looked hard. No pulsar detected. No X-ray signature. Maybe it's there, hidden, buried in dust, debris blocking our view. Or maybe it formed a black hole, directly. No bounce, just collapse, straight through. We don't know. The missing remnant, still unsolved. 37 years later, but there are hints. Recent observations. ALMA, infrared, a blob, center of the remnant. Could be dust, warm dust, heated by something. Compact object maybe, accreting material, generating heat. Or could be radioactive decay. Isotopes, still glowing. We're not sure. The data is ambiguous. We need more. Better resolution, longer wavelengths. James Webb maybe, or future telescopes. Extremely large telescope, coming online soon. Might resolve it. Find the core, Solve the mystery. SN 1987. A keeps teaching us, even now, it's a gift. A nearby explosion, well documented, monitored continuously. We'll study it for generations, compare models, test theories, understand physics, extreme conditions, densities, temperatures, magnetic fields. Nothing else comes close. But what about the future? Could a supernova threaten Earth? It's possible, theoretically, if one exploded close enough, within 30 light years maybe. The radiation, gamma rays, X-rays, could damage our atmosphere, strip the ozone layer, increase UV exposure, harm life, or the cosmic rays, high-energy particles, accelerated by the shock, bombarding Earth, for centuries, affecting climate, causing mutations, mass extinctions even. Some researchers think this happened. Past extinctions correlate with supernova timing. Isotopes in rock layers, iron-60, doesn't occur naturally, comes from supernova, found in ocean sediments 2 million years ago. Evidence of a nearby explosion, Scorpius-Centaurus Association, group of stars, about 400 light-years away. One of them exploded, close enough, deposited iron-60 on Earth. Did it affect life? Hard to say. The Pliocene epoch, climate changes, some species disappeared. Coincidence? Maybe. Or cause and effect? We don't know. But currently, we're safe. No massive stars nearby. Betelgeuse is close, 650 light-years. Will explode, someday. Could be tomorrow. Could be 100,000 years. But it's far enough. Won't hurt us. Just spectacular. Brighten the sky. Visible during the day. Outshine the moon. For weeks. Maybe months. Then fade. Gradually. Over years. Leaving a nebula. Expanding remnant. Future astronomers, hundreds of years from now, will study it, like we study Cassiopeia A, Crab Nebula. But we'll see it happen, live, real time. What would it look like? Predictions vary: brightness, duration, color. Betelgeuse is red, cooler star. The supernova might have a reddish hue, initially, then blue-white as it heats up. The light curve, rise and fall. Over months, we'd track it. Spectroscopy, measure composition, expansion velocity, asymmetries. It would dominate astronomy. For years, every telescope pointed at it. Professional, amateur, students, everyone. A once-in-civilization event, and it's coming. Question is when. Could you see a supernova right now? Probably. With a telescope. They happen constantly. In distant galaxies, automated surveys find dozens weekly. Zwicky Transient Facility, ZTF, scans the sky. Every night, compares images, looks for changes, new points, brightening. Most are supernovae, thousands discovered. Every year, classified, spectra taken, redshifts measured, distances calculated, added to databases. Available to researchers worldwide. This is modern astronomy, big data, automated, fast, within hours, discovery, classification, follow-up, coordinated, telescopes, around the world, space-based, ground-based, different wavelengths, optical, infrared, ultraviolet, X-ray, radio, full picture, multi-wavelength. The data is staggering. Light curves, thousands of them, each one unique, slightly different, different progenitors, masses, compositions, environments. We analyze them, statistically, look for patterns, correlations, brightness versus decay rate, spectra versus peak luminosity. This is how we refine models, test predictions, understand diversity, and diversity there is. Supernovae come in flavors. We've mentioned types, Ia2, IBIC, but within those, subtypes, 2, P plateau, flat light curve, 2L, linear, steady decline, 2B shows helium, 2N, narrow lines, interacts with circumstellar material. Each tells a story. Different progenitor, different death, different physics. Type 1A are the strangest. Thermonuclear, white dwarf, accretes matter, reaches critical mass, 1.4 solar masses, Chandrasekhar limit, carbon ignites, runaway fusion, entire star, obliterated, no remnant, just debris, expanding, glowing, powered by radioactive decay, nickel 56, cobalt 56, iron 56. This decay produces light, the glow, for months. The light curve, very consistent. Type 1A, all similar. Same mass, same explosion, same brightness, peak luminosity. Known, makes them standard candles. Measure apparent brightness. Calculate distance. This is how we discovered. Dark energy. 1998. 2 teams, studying distant Type 1A, expected them to be certain brightness, but they were dimmer, farther away than predicted. Universe expanding, faster, accelerating, not slowing. As expected, gravity should decelerate, pull everything back. But no, expansion speeding up, something pushing. Dark energy, mysterious, unexplained, makes up 70% of the universe. We don't know what it is, just that it's there. Accelerating expansion. Supernovae told us this. Type 1A, standard candles, revealed the universe's fate. It will expand, forever, faster, galaxies receding, eventually, beyond our horizon, unreachable, universe becoming emptier, colder, darker, heat death, trillions of years, from now, but certain. Unless something changes, dark energy evolves, unlikely but possible. We're still measuring, more supernovae, better data, refining models, understanding acceleration, how it changes, over time, the equation of state, of dark energy, critical parameter, tells us, future, fate, everything, and supernovae are the key. They probe cosmic history, expansion rate, at different epochs, near, far, early universe, recent, build a timeline, map expansion, understand dark energy. This is cosmology, driven by explosions, stellar deaths, across billions of years, light reaching us. Now, from when? Universe was young, half its current age. Third, we measure, compare, learn. The universe's story, written in supernovae. But there's something else, something we haven't touched. The sound. You can't hear explosions. In space, no medium. Sound needs air, molecules, vibrating, transmitting pressure waves. Space is vacuum, empty, silent. But supernovae create pressure waves, in gas, nebulae, surrounding material. These waves travel, compress, heat. We can detect them. Radio telescopes, measure density fluctuations, map them, convert to sound, sonification. NASA does this, takes data, X-ray, radio, infrared, maps brightness, position, over time, converts to audio, pitch, volume, tone. You can listen to supernova remnants. Cassiopeia A, Crab Nebula. They have voices, eerie, haunting, beautiful, whistles, rumbles, tones rising, falling. It's not real sound, not what you'd hear if you were there, because you'd hear nothing. But it represents the data, the physics, waves propagating, energy distributing, structure forming, and it's moving, emotional even, to hear the death cry of a star translated into something we can perceive. Our brains process sound differently than images, patterns, rhythms, changes. We notice things we'd miss. In pictures, sonification is a tool, scientific, but also artistic, communicative. It brings the universe closer, makes it relatable, human. Because these events, supernovae, they're violent, destructive, cataclysmic, but also creative, generative, beautiful. They end and begin, destroy and create, death and birth all at once. And we're drawn to that, the duality. We understand it instinctively. Everything in life carries this tension, endings that seed beginnings, loss that enables gain. Supernovae embody this truth on cosmic scale. But let's talk about something we haven't fully explored: the observers, the humans who study these events, the astronomers staring into darkness, waiting, hoping for stars to die. It sounds morbid, maybe it is, but it's also essential. Because supernovae don't announce themselves, they just happen. Somewhere, in some galaxy, among billions of stars, one goes. And if we're not watching, we miss it. Gone. The light fades. Evidence disappears. Opportunity lost. So astronomers scan every night, automated telescopes, surveys, photographing patches of sky repeatedly, comparing images, looking for changes, new points of light where there was nothing before. It's tedious, computational, mostly. Algorithms flag potential candidates, then humans check, confirm, classify, measure, follow up. Some nights, nothing. Weeks, months, then alert, new transient, brightening rapidly. Could be supernova, could be something else, asteroid, variable star, camera glitch, cosmic ray, needs verification, spectroscopy, reveals the truth, elements present, velocities, expansion, temperature, the signature, unmistakable. It's a supernova, and the clock starts, because supernovae evolve quickly. At first, the light curve rises, peaks, then declines, different rates, depending on type. Type 1a, rise in weeks, peak, stay bright, month or so, then fade, gradually, over months, powered by radioactive decay, predictable. Type 2, more varied. Some rise fast, peak quickly, fade faster. Others, plateau, stay bright, longer, then drop. Each one, unique, but patterns emerge. Classifications help, but observation is everything. The more data, the better. Multiple wavelengths, X-ray, ultraviolet, optical, infrared, radio. Each reveals different physics, different layers, different processes, shock heating, radioactive glow, dust formation, interaction with surrounding material, all happening simultaneously, overlapping, competing, creating the signal. We observe, and timing matters. Early observations, crucial. The first hours, days, capture processes. We can't see. Later, the shock breakout, that initial flash, when the shockwave bursts through the star's surface. It's brief, hours at most, mostly X-ray, ultraviolet, difficult to catch, requires luck, and fast response. SN 2024, GGI, caught early, just 26 hours. After first detection, Yang, astronomer, pointed the VLT, very large telescope, at it immediately, got spectra, imaging, captured the early, evolution, saw something remarkable. The explosion wasn't spherical, it was olive-shaped, elongated, asymmetric. The progenitor, red supergiant, 12 to 15, solar masses, radius 500 times. The sun, huge, and when it exploded, the blast emerged unevenly, not uniform, one direction, stronger, faster than others. Why? We don't know. Exactly. Maybe rotation, magnetic fields, asymmetries in the core, convection, instabilities. Stars aren't perfect spheres. Inside, they're turbulent, roiling, convective cells, rising, falling, mixing, and when they collapse, that chaos amplifies. The core bounces, but not symmetrically. The shock propagates irregularly. Jets can form, matter streams, outward, preferentially, along poles or equators. Depending on conditions, we're learning that asymmetry is common, not the exception. Most supernovae are lopsided. To some degree, we see it in remnants. Cassiopeia A, clearly asymmetric, debris moving faster, one side than the other, knots, filaments, jets, all evidence of complex explosion geometry. And this matters for understanding the mechanism. How exactly does the shock revive after stalling in core collapse? It's a problem. The bounce shock loses energy, dissociates nuclei into protons, neutrons, endothermic, absorbs energy, shock weakens, stalls at a few hundred kilometers from the core. So how does it restart, break through, eject the star? Neutrinos. The answer, probably. The core collapses into neutron star or black hole. Incredibly hot, radiating neutrinos, trillions per second, 10 to the 58 in total. Most escape straight through everything, but a tiny fraction, maybe 1% less, interacts with matter behind the shock, deposits energy, heats it, drives convection, turbulence, and this revives the shock, pushes it outward, explodes the star. This is the theory. Neutrino-driven explosion, supported by simulations, three-dimensional models showing how convect ion turbulence asymmetry help the shock succeed. But we're not certain. Observations of neutrinos from Supernovae, rare, SN 1987A, only one detected with neutrinos, 25 events total from 2 detectors. In 1987, supernova in Large Magellanic Cloud, 160,000 light-years away, close for supernova, and we detected neutrinos hours before. Optical signal, because neutrinos escape immediately. Core collapse happens. Neutrinos stream out, light speed, through the star, out into space. Light trapped inside. Dense envelope takes time to diffuse. Hours, days, eventually breaks free. We see it. But neutrinos, already gone, arrived earlier. This is powerful. Early warning system. If we detect neutrino burst from direction in sky, we know supernova happening right now. Point telescopes immediately catch the rise, the breakout, everything. Future neutrino detectors, larger, more sensitive. Ice cube at South Pole, detecting high energy neutrinos, not supernova energy range, but others. Hyper Kamiokande in Japan, successor to Super Kamiokande, bigger, better, will detect galactic supernovae easily. Thousands of neutrinos. If one goes off in Milky Way, we'll know immediately. Alert the world. Every telescope turns, watches. It'll be incredible. Once in lifetime event for astronomy. The last galactic supernova visible to naked eye was 1604, Kepler's supernova, over 400 years ago. We're overdue, statistically. Milky Way should have a few per century. We haven't seen 1 in 4 centuries. They've happened, probably, just on far side. Galaxy, hidden by dust, obscured. We can't see through. Galactic plane, thick with gas, dust, blocks, optical light, but infrared, radio, X-ray penetrate. We've found remnants, recent, relatively. Cassiopeia A exploded around 1680, approximately, but no record of observation. Too faint, or hidden, or missed. Unlucky. When will the next galactic supernova occur? We don't know. Could be. Tomorrow. Could be. 100 years. Could be. 1,000. Random. Unpredictable. But candidates exist. Betelgeuse. Famous. Red supergiant. In Orion. 10 to 20. Solar masses approaching end of life. could explode anytime, next million, years, or tomorrow. We don't know exactly. Its mass, uncertain. Evolutionary state, unclear. Its variable, dims, brightens. In 2019, dimmed dramatically. Speculation. Was it going supernova? No. Turned out, dust cloud, ejected material, blocking light, temporarily. It recovered. Betelgeuse is still there, for now, but someday it will explode, and when it does, it'll be spectacular, visible, daytime, bright as, quarter moon, maybe brighter, depending on details. It's only 650 light years away, approximately, close, cosmically speaking, safe for Earth, far enough, radiation won't harm us, but close enough to study in detail every wavelength, every instrument pointed at it, learning everything we can about core collapse in real time. Imagine that, the data, the insights, it would revolutionize our understanding, supernova physics, stellar evolution, nucleosynthesis, everything, and it's coming. Someday, we just don't know when. Meanwhile, we watch other galaxies, distant stars, dying, millions, billions, light years away, their light reaching us. Now, from when universe was younger, we're seeing the past, learning history of stars across time, supernovae in young galaxies, different metallicity, lower, fewer, heavy elements, stars formed from more primordial gas, hydrogen, helium, little else. These stars burn differently, explode differently. Maybe we're testing models, predictions against observations. James Webb Space Telescope found supernova from when universe only 730 million years old. SN in GRB 250314A associated with gamma ray burst, extremely energetic, long duration, burst, sign of massive star, collapse, and Webb detected it, imaged, host galaxy, measured, properties. This is era of reionization, first stars, galaxies, emerging, ionizing, neutral hydrogen, filling, universe, supernovae, played role in this, enriching, gas with metals, oxygen, carbon, iron, seeding, next generation, stars, planets, life. Eventually, these ancient supernovae are ancestors to everything we see today, including us, the iron in your blood, forged in supernova, billions of years ago, ejected into space, mixed with gas, collapsed into new star, sun, planets, formed, Earth, cooled, life, emerged, evolved. Here you are, made of stardust, literally supernova ash. It's poetic, but also factual. Carl Sagan said it. We are star stuff, contemplating stars. And he was right. Every atom, heavier than helium, in your body came from stellar nucleosynthesis, most from supernovae, the calcium, in bones, oxygen, you breathe, carbon, in DNA, nitrogen, in proteins, phosphorus, sulfur, all forged in stars, dispersed by explosions. Supernovae are not just destruction, they're creation, engines, cosmic recycling, plants. Death gives life, literally. Without supernovae, no heavy elements, no planets, no chemistry, complex, enough for life. Universe would be hydrogen, helium, boring, sterile, dark, but supernovae change that, enriched cosmos, made diversity possible, and they continue. Every supernova adds to the galactic inventory. Metals, slowly, increasing, metallicity, over time, early universe, low, metallicity, now, higher, sun has about 2%, metals by mass, rest, hydrogen, helium, but that 2%, critical, planets, formed, from it, life, depends, on it, and it's all, from stars, dying, exploding, scattering, their guts across space and time. This cycle continues, will continue, as long as stars form, die, billions of years into future, until star formation ceases. Eventually, universe expands. Too much. Galaxies isolated. Gas depleted. Used up. No more. Stars form. Existing stars burn out. Die. White dwarfs. Neutron stars. Black holes left behind. Cold. Dark. Remnants. No more. Supernovae. No more. Light. Just darkness. Expanding forever. Heat death. Trillions of years away. But inevitable. Unless something changes. We don't expect it to. Dark energy. Accelerating. Expansion. Continuing. Universe headed toward cold, empty, end. Supernovae told us. This. Type 1a. Standard candles. Measured distances. Redshifts. Discovered. Acceleration. 1998. Nobel Prize. 2011. Saul Perlmutter. Brian Schmidt. Adam Rees. Recognized for this. Discovery changed cosmology forever. Before we thought universe might recollapse, big crunch, or expand. Forever, coasting, slowing, but still expanding. Now we know it's accelerating. Dark energy dominates. Future is expansion, isolation, darkness. Supernovae revealed this fate, their light carrying messages across cosmic time. And we listen, measure, learn what the universe is telling us about itself, its history, its future, and our place within it. But let's bring this story closer to something you can almost touch. Your body right now. This moment contains fragments of dozens, maybe hundreds, of different supernovae. Each atom with heavier nucleus than helium came from a star that died violently. The iron in hemoglobin carrying oxygen through your bloodstream forged in. Core collapse. Supernova, maybe 6 billion years ago, maybe more. Recently, that particular iron atom has been recycled through multiple generations of stars, planets, cosmic dust, before ending up in you temporarily, because you'll return it eventually back to Earth, back to cosmic cycle. Nothing is permanent except the cycle itself, the calcium, strengthening your bones right now. Different supernova, different time, different place in galaxy, but same process. Silicon burning in massive star's core, final hours, creating calcium, then explosion, scattering it across light years, mixing with other material, collapsing into new stars, planets forming, Earth growing, life emerging, evolving, until that calcium ended up in you, supporting your skeleton. As you read this, think about that. Every element playing essential role in your biology has history stretching back billions of years, across vast distances, through violent deaths and gentle births. The phosphorus in your DNA, backbone, supernova origin. Without it, no DNA, no genetic code, no heredity, no evolution, no life as we know it. Supernovae made that possible. The sulfur in proteins, supernova. The chlorine in cells, supernova. Even trace elements, zinc, copper, selenium, tiny amounts, but crucial for enzymes, for metabolism, for life. All supernova products. You are literally walking, talking, thinking. Supernova remnant, not poetic exaggeration. Scientific fact, chemical analysis confirms it. We know where elements come from, most from supernovae, some from other processes, but bulk of heavy elements, stellar explosions. This means something profound about connection between us and cosmos. We're not separate from universe, observing it from outside. We're part of it. made from, it intimately connected to its history, its processes, its evolution. When you look at stars, you're looking at relatives, distant ones, but relatives nonetheless. Same material, same origins, same cosmic story. Carl Sagan understood this deeply. His phrase, star stuff, contemplating stars, captures it perfectly. But there's more to this story than just our composition. Supernovae shaped solar system in ways beyond just providing elements. Evidence suggests that supernova might have triggered solar systems formation about 4.6 billion years ago. Cloud of gas and dust floating in Milky Way, mostly stable, not collapsing, just drifting. Then something disturbed it, compressed it. Shockwave perhaps. From nearby, supernova, compression triggered, gravitational collapse. Cloud began contracting, spinning, flattening into disk. At center, sun formed in disk. Planets grew from dust and gas, including Earth. We have evidence for this supernova trigger found in meteorites, primitive ones, formed early in solar system history. They contain short-lived radioactive isotopes like aluminum, 26, half-life, only 700,000 years, shouldn't exist. In meteorites, billions of years old, unless it was created shortly before solar system formed, and only one known process creates aluminum-26 in large quantities, supernova nucleosynthesis. So, supernova exploded nearby, perhaps 10 light years away, injected fresh radioactive material into cloud, shockwave compressed, cloud triggered collapse, solar system began forming. We owe our existence not just to material from supernovae, but possibly to supernova triggering solar systems birth. Without that explosion, cloud might never have collapsed. No sun, no planets, no Earth, no us. Of course, this is hypothesis, not proven definitively, but evidence is strong, and it's beautiful idea that violent death of star light years away, billions of years ago, led directly to our existence, cause and effect across cosmic scales. This brings us to bigger question: how common are supernovae in galaxy? How often do they happen? Current estimates suggest Milky Way experiences about 2 to 3 supernovae per century on average. Sounds rare, but consider galaxy has hundreds of billions of stars and has existed for billions of years. Total number of supernovae in Milky Way's history is enormous, hundreds of millions, perhaps billion or more, each one enriching galaxy with metals, each one contributing to galactic chemical evolution. Over time, metallicity increases. Early universe, almost pure, hydrogen, helium, first stars, population 3, no metals, they lived, died, exploded, enriched gas. Next generation, population 2, low metallicity, but some metals present, they lived, died, exploded, further enrichment. Current generation, population 1, sun is population 1, higher metallicity, about 2% metals, enough to form rocky planets, support complex chemistry, enable life. This progression took billions of years, countless supernovae, gradually building up inventory of heavy elements, and it's still ongoing. Every supernova today adds to total galactic metallicity, continues rising slowly over cosmic time. Eventually, star formation will cease, gas will be depleted, no more stars born, existing stars will die, last supernova will occur, then silence, no more explosions, just remnants, white dwarfs, neutron stars, black holes, cooling, fading, forever. But that's trillions of years away. For now, supernovae continue, shaping galaxy, enriching it, driving its evolution, and occasionally, they're visible. From Earth, naked eye, supernovae, throughout history, humans have witnessed them. Ancient Chinese astronomers kept detailed records, guest stars appearing suddenly, fading slowly, over weeks or months. First recorded, supernova, year 1, 85 AD. Chinese astronomers noted it, visible for 8 months. Modern astronomers identified remnant, RCW80, 6, in southern sky, another famous 1, year 1, 006 AD, supernova 100, brightest supernova in recorded history, visible magnitude -7.5, brighter than Venus, visible during daytime for weeks, night sky for months. Multiple cultures recorded it: China, Japan, Egypt, Europe, possibly Americas. Remnant still visible today, expanding shell of gas, beautiful structure. Then year 1054, July 4th, Crab Nebula, supernova. Chinese, Japanese, Arab astronomers recorded it, visible in daylight for 23 days, night sky for 653 days, nearly 2 years. Remnant is Crab Nebula, one of most studied objects in astronomy. Contains pulsar, spinning neutron, star, rotating 30 times per second, emitting beams of radiation like cosmic lighthouse. Remarkable object. More recent, supernova 1604, Kepler's supernova. Johannes Kepler observed it. Last supernova, visible to naked eye, in Milky Way, over 400 years ago. We're overdue for another, statistically speaking, but galaxy is big. Most supernovae happen far away, obscured by dust, interstellar material. We don't see them, invisible light, but we detect them. Other wavelengths, radio, X-ray, infrared, and we see plenty in other galaxies. Every year, hundreds discovered, thousands even, with modern surveys, automated telescopes, scanning sky nightly, looking for transients, new objects appearing. Supernovae show up regularly, each one studied, analyzed, adding to our knowledge. One supernova changed everything. Supernova 1987A, February 1987, visible from southern hemisphere in large Magellanic Cloud, small galaxy orbiting Milky Way, about 160,000 light-years away, closest supernova since Kepler's, and first observed with modern instruments, telescopes, detectors, neutrino observatories, everything. It was gold mine of information. Before optical light arrived, neutrinos detected. 3 different neutrino observatories around world detected burst of neutrinos about 3 hours before optical brightening. Why? Because neutrinos travel nearly light speed, interact weakly with matter. They escape star's core immediately during collapse. Light photons trapped inside dense stellar material takes hours, sometimes days, to diffuse outward, reach surface, escape. So neutrinos arrive first. Early warning system for supernovae. Supernova 1987A25, neutrinos detected. Total doesn't sound like much, but considering how weakly neutrinos interact, detecting any is remarkable. Those 25 neutrinos told us enormous amount about core collapse process, energy released, neutrino flavors, timing, everything matched. Theoretical predictions, beautifully confirmed models of core collapse. Supernovae validated decades of theoretical work. It was triumph for astrophysics and supernova 1987 are kept giving. Over years, decades, astronomers watched remnant expand, saw rings of material ejected before explosion, lit up by shockwave, saw elements being created, detected radioactive decay of cobalt-56 into iron-56, powering light, curve, studied pulsar or neutron, star left behind, learned about, progenitor star, blue supergiant, about 20, solar masses, everything about, supernova 1987A, advanced our understanding enormously. And it's still being studied today, over 35 years later. Remnant continues evolving, new features appearing as shockwave interacts with surrounding material. Its gift that keeps on giving. Now, we wait for next nearby supernova in our galaxy or close neighbor. When it happens, we'll be ready. Network of telescopes, neutrino detectors, gravitational wave observatories, all coordinated, all watching. We'll capture it in unprecedented detail. Every wavelength, every messenger, neutrinos, photons, maybe even gravitational waves. If conditions right, it will be spectacular, scientific event of lifetime. But when will it happen? We don't know. Could be tomorrow, could be 100 years from now. Stars don't announce their deaths in advance. Well, some do. Betelgeuse, red supergiant in Orion, about 700 light years away. It's nearing end of life, could explode anytime, astronomically speaking. Could be tomorrow, could be 100,000 years from now. We don't know precisely, but when it does, it will be bright, visible during day, for weeks, night sky, for months, brighter than full moon. Perhaps it will be spectacular sight and completely safe. 700 light years too far to harm Earth. We'll just enjoy show, learn everything we can. Another candidate, Eta Carinae, massive binary system, about 7,000 light years away. One star, over 100 solar masses, extremely unstable, had eruption in 1840s. Great eruption, ejected huge amount of material, created spectacular homunculus nebula, visible today. Eta Carinae could go supernova soon, or might be thousands of years. Still, we watch it closely, because when it explodes, it will be visible from Earth, potentially very bright. These are just two examples. Many massive stars in galaxy are candidates for future supernovae. We monitor them, study them, try to predict, but prediction is difficult. Stars are complex, final stages uncertain. So we wait and watch, and when next one happens, we'll be there, recording it, learning from it, adding to our understanding of these cosmic catastrophes that paradoxically create rather than just destroy. Until that moment arrives, let's reflect on what supernovae mean for existence itself. These explosions aren't just spectacular light shows in distant corners of the universe. They're foundational events that made everything possible, including you. Every breath you take contains oxygen from supernovae. Every heartbeat, powered by iron from stellar cores, calcium in your bones, carbon in your DNA, nitrogen in proteins, all forged in stars, scattered by explosions. We are literally made of star stuff, as Carl Sagan said. But more specifically, we're made of supernova stuff. Think about that for a moment. Billions of years ago, star somewhere in galaxy reached end of life, collapsed, exploded, scattered elements into space. Those atoms drifted through interstellar medium, eventually condensed into new stars, planets. One planet became Earth. Those atoms became part of oceans, mountains, atmosphere, life. You're carrying atoms right now that were inside dying star. Experienced temperatures of billions degrees were accelerated to fraction of light speed, traveled through space for eons, found their way here into you. It's profound connection to cosmos, not metaphorical, not poetic, exaggeration. It's literal, physical fact. Your body is recycled, stardust, supernova remnants, walking around, thinking, feeling, wondering about their origins. But supernovae do more than create elements. They trigger star formation. Compression from shockwaves can cause molecular clouds to collapse, form new stars. Our sun might have been born this way, triggered by nearby supernova billions of years ago. Evidence suggests this. We find isotopes in meteorites that could only come from supernova present when solar system formed. Short-lived radioactive isotopes like aluminum 26, half-life just 700,000 years, found in oldest meteorites, must have been injected into solar nebula right before or during formation. Where could it come from? Nearby supernova explosion enriched cloud with fresh, heavy elements, including radioactive ones. Shockwave compressed cloud triggered collapse. Sun and planets formed. We exist because supernova happened at right place, right time, nearby enough to enrich our cloud, not so close to destroy it. Timing had to be perfect. Too early, isotopes would have decayed. Before incorporation, too late. Solar system already formed, but it happened just right. Goldilocks supernova that made us possible. This raises a fascinating question. How common is life in universe if it requires such specific conditions? Needs supernova to create elements, but not too close, not too far, just right. Enrichment, just right. Timing, given billions of stars in galaxy, trillions of galaxies in universe, countless supernovae happening. Odds seem good that right conditions occur many places. Maybe life isn't rare, maybe it's inevitable. Given enough stars, enough time, enough supernovae. We don't know yet, but studying supernovae helps us understand requirements for life, where elements come from, how they're distributed, what conditions needed for planets to form. Supernovae also shape galaxy structure, energy they release. Heats interstellar medium, creates bubbles, cavities, drives galactic, winds, material ejected from galaxy entirely, sometimes affects star formation rates, galaxy evolution in small galaxies. Especially supernovae can blow out significant fraction of gas, halt star formation for long periods. Galaxies too small to hold onto gas against supernova explosions. Stay small, don't form many stars. In larger galaxies like ours, supernovae create feedback loops, regulate star formation. Too many stars forming means more supernovae, which heats gas, slows formation. Too few stars means fewer supernovae. Gas cools, formation increases. It's self-regulating system. They're also major source of cosmic rays, high energy particles, mostly protons, that zip through galaxy at near light speed. Where do they come from? Shockwaves from supernova remnants accelerate particles to enormous energies. Cosmic rays have effects on Earth. They create isotopes in atmosphere, like carbon-14, used for dating. They cause mutations in DNA, contribute to evolution. They might even affect climate by influencing cloud formation. Hypothesis still debated, but possible. So supernovae influence Earth even now, not just in past when they created elements, but ongoing through cosmic rays they produce. And then there's dark energy, type 1a supernovae. Remember, standard candles, same brightness, wherever, whenever. They explode by measuring apparent brightness. We determine distance by measuring redshift. We determine recession velocity. In 1990s, 2 teams did this for distant type 1a supernovae expected to find universe expansion slowing down. Gravity should pull everything together, slow expansion. Instead, they found opposite, universe expanding faster now than past, expansion accelerating. This was shocking, completely unexpected. Won Nobel Prize in 2011. What could cause this? Some form of energy permeating space, pushing everything apart. They called it dark energy. We still don't understand what it is, but it's real, and it's 70% of universe discovered through supernovae, type 1a explosions, billions of light years away, told us something fundamental about cosmos, universe not only expanding but acceleration, fate of universe to expand forever, growing colder, darker, more empty. Eventually, that's far future, trillions of years away, but supernovae revealed it, changed cosmology forever. Now, let's come back to present what happens when we detect supernova. Today, alert systems constantly scanning sky, automated telescopes taking images, comparing to previous images, looking for new points of light. When one appears, alert goes out within minutes. Astronomers worldwide notified, telescopes swing into action, ground-based, space-based, radio, optical, X-ray, gamma ray. Everyone wants piece of data. Follow-up observations begin immediately. Spectra taken to classify, type, light curves measured to track evolution. Neutrino detectors checked for signals if close enough. Gravitational wave observatories listen for signals from neutron star mergers, which also produce explosions. Data shared openly, rapidly. Astronomy community works together on transients, time sensitive, can't wait for publications, need data now to coordinate observations, understand what's happening. It's beautiful example of science working as should. Collaboration, open sharing, collective effort to understand universe, and what we learn is incredible. Each supernova different, even same type, shows variations, tells us about progenitor, star, environment, explosion mechanism. We're learning how massive stars die, what determines whether core collapses to neutron, star, or black hole, how much mass ejected, how elements distributed. Recent observations, particularly interesting. Supernova 2024 GGI detected April 2024, observed just 26 hours after discovery. Very quick. Astronomers found shockwave breakout, looked olive shaped, not spherical. As expected, star wasn't symmetric when it exploded. Tells us something about final moments before collapse. Maybe rotation, maybe convection, maybe magnetic fields. We're still figuring out. Every new observation adds piece to puzzle, refines models, challenges assumptions. That's how science progresses. Observation, theory, back and forth until we converge on truth. But some mysteries remain. How exactly does explosion Mechanism work. In core, collapse supernovae. Models show that initial shock from bounce, stalls, shouldn't make it out, shouldn't explode, star. But they do explode, obviously. So something else must be happening. Current leading theory, neutrinos, massive flux of neutrinos from proto-neutron star usually pass through matter easily, but flux so intense, so dense, that small fraction get absorbed by stalled shock, deposits energy, revives shock, drives explosion. It's called neutrino-driven mechanism, seems to work in simulations, matches observations, but details still uncertain. Computer models incredibly complex, three-dimensional, turbulent, magnetic fields, rotation, nuclear physics, neutrino transport, all interacting. We're getting better at simulations, more computing power, better physics input, but still not perfect, still uncertainties. That's okay. That's science. We don't know everything yet. That's what makes it exciting. There's still more to discover. Another mystery, supernova remnants. Some symmetrical, some not. Some show jets, some don't. Why? What determines? Structure probably depends on progenitor, star, explosion mechanism, surrounding environment, but exact relationships unclear. We're studying remnants in detail. X-ray observations show hot gas. Radio observations show magnetic fields, cosmic rays. Optical observations show filaments, knots. Infrared shows dust, molecules, all pieces of puzzle. Young remnants like Cassiopeia A, particularly interesting, only about 350 years old, still expanding rapidly, about 1 million kilometers per hour, one of fastest shock waves ever observed, shows asymmetries. Jets suggests explosion, wasn't spherical, maybe star, rotating, maybe jets, formed during collapse, punched through poles, created asymmetric remnant. We're watching it change in real time, comparing images from years apart, seeing expansion, seeing features evolve. It's living laboratory for studying supernova physics. Older remnants like Crab, Nebula, different story, about 1,000 years old, expanding slower, but still active, has pulsar in center, spinning 30 times per second, powering nebula with relativistic wind, creates beautiful, complex structure. Crab pulsar, neutron star, left over from supernova 1154, observed by Chinese, Japanese, Arab astronomers, recorded as guest star, visible during day for weeks, night for months. Today we see remnant glowing brightly across electromagnetic spectrum, radio to gamma rays, powered by pulsar, slowing down, converting rotational energy into radiation, particle acceleration. It will eventually fade. Pulsar will slow, stop radiating. Nebula will disperse into interstellar medium, enriching it with heavy elements from supernova. Cycle continues. That's beauty of supernovae. They're not end, they're beginning. End of star, but beginning of enrichment, of new star formation, of planets, of life. Eventually, every atom in your body except hydrogen was made in star or supernova. Your end result of billions of years of cosmic evolution, stellar birth, death, rebirth. Next time you look up at night sky, remember, stars you see will someday die. Massive ones. In supernovae, they'll scatter elements into space. Those elements will form new stars, new planets, maybe new life, and somewhere billions of years from now, being made from atoms created in supernova. Happening today might look up at their sky, wonder about their origins, just like you. That's legacy of supernovae, not just destruction, creation, not just death, but life. They connect past to future, stars to planets, cosmos to consciousness. So when next nearby supernova happens, whether Betelgeuse or Eta, Carinae or unknown star, don't just see it as distant explosion, see it as cosmic forge, creating elements that will someday become part of new worlds, new beings, new stories. You're part of that story right now, made of supernova remnants from past, living on, planet enriched by stellar deaths, looking out at universe that continues to evolve through same processes. That's what supernovae teach us. We're not separate from universe, we're part of it, products of it, participants in ongoing cosmic story of creation, destruction, transformation. Every supernova that happens anywhere in universe adds to that story, creates new elements, triggers new star formation, shapes galaxy, evolution, influences cosmic structure, and we're here to witness it, study it, understand it, appreciate it. That's privilege and responsibility to learn everything we can about these magnificent explosions that made us possible. The universe speaks through supernovae, tells us about stellar evolution, nuclear physics, cosmic history, our own origins. All we need to do is listen. So here we are, at the end of this cosmic journey through stellar death and rebirth. We've traced supernovae from their violent beginnings through their spectacular endings, from collapsing cores to expanding debris fields, from neutrino bursts to element creation. But what does it all mean? Let me tell you what strikes me most about supernovae. It's not their brightness, not their power, not even their violence. It's their generosity. Think about it. A star spends millions of years building up elements in its core, layer after layer. Hydrogen, helium, carbon, oxygen, silicon, iron, creating complexity from simplicity, building heavier elements through patient fusion. Then, in its final moments, it gives everything away, doesn't keep anything, doesn't hoard its treasures, just explodes, scatters everything it created across light years of space, seeds the galaxy with the building blocks of planets, of life, of you. That's profound selflessness. On cosmic scale, your body contains atoms from dozens of different supernovae, maybe hundreds. Each one died billions of years ago. Each one contributed something essential. Calcium from one, iron from another, oxygen from a third, all assembled in you, temporarily, because you'll give those atoms back eventually. Return them to Earth, to the cosmic cycle. Someday, they'll be part of another star, another planet, maybe another being, looking up at their sky, wondering about their origins. That's the real story of supernovae, not destruction, transformation, not endings, transitions. They're bridges between stellar generations, connecting past to future, old stars to new worlds. Without them, no complexity, no chemistry beyond hydrogen and helium, no rocky planets, no water, no organic molecules, no life. The universe would be simple, boring, empty. But supernovae changed that. They enriched the cosmos, made diversity possible, made us possible. Every breath you take contains oxygen from supernovae. Every heartbeat pumps iron created in stellar cores. Your bones are built from calcium forged in dying stars. Your thoughts flow through neurons using elements scattered by explosions billions of years ago. You're not just made of star stuff. You're made of supernova stuff. The most violent creative force in the universe runs through your veins. That connection to the cosmos, to these distant explosions. It's not metaphor, it's physics, chemistry, biology, all intertwined, and it continues. Right now, somewhere in the universe, a star is collapsing, building towards supernova. In a few hours, days, years, it will explode. Scatter fresh elements into space. Start the cycle again. Maybe those elements will drift through space for millions of years. Eventually condense into new stars, new planets. Maybe someday, far in the future, those atoms will be part of living beings, looking up at their sky, asking the same questions we ask. Where did we come from? What are we made of? Why are we here? The answers lead back to supernovae. Always, we're still learning. Every new observation teaches us something. SN 2024 GGI with its olive-shaped blast. SN 1987 A with its neutrino burst and mysterious missing remnant. Each one unique. Each one revealing new physics. Future supernovae will teach us more. When Betelgeuse explodes, whenever that happens, we'll watch it in unprecedented detail. Every wavelength, every messenger, neutrinos, photons, maybe gravitational waves. It'll revolutionize our understanding. But we already know enough to appreciate what supernovae mean. They're not just astronomical events, they're cosmic necessity. Without them, universe stays simple, hydrogen and helium forever. With them, complexity emerges, chemistry develops, life becomes possible. They're destructive and creative simultaneously, ending and beginning in same moment. That duality, that paradox, it's beautiful, profound, because life works the same way. Endings enable beginnings, death feeds life, nothing lasts forever, but everything transforms, continues in different form. Supernovae embody this truth on grandest scale. Star dies, galaxy lives, elements scatter, new worlds form. Consciousness emerges from stellar ashes, looks back at the process that created it, marvels at its own existence. That's where we are right now. Products of supernovae, made from their remnants, studying them, understanding them, appreciating them. It's circular, recursive, self-referential, the universe examining itself through us. Supernovae creating the observers who observe supernovae. Carl Sagan said, "We're star stuff contemplating stars." He was right. But more specifically, we're supernova remnants contemplating supernova, the explosions that made us possible. There's poetry in that, science and beauty intertwined. When you look up tonight, at the stars scattered across the darkness, remember, some of them will explode, someday, scatter their contents across space, enrich the galaxy further, trigger new star formation, continue the cycle, and atoms from those explosions, billions of years from now, might become part of something wonderful, something alive, something conscious, something asking questions about its origins, just like atoms from ancient supernovae, long gone, long forgotten, became part of you. That's the legacy, the gift, the meaning of supernova, not destruction, creation, not death, life, not endings, transformations that never truly end. The universe recycles everything. Nothing is wasted, nothing is lost, just transformed, redistributed, reborn in different forms. Supernovae are the engines of this transformation, cosmic forges, stellar phoenixes, rising from their own ashes to create something new. And you're proof it works. Standing here, breathing, thinking, wondering, made entirely from the ashes of dead stars, from supernova remnants that drifted through space for eons before finding their way to Earth, into you. That's not just science. That's miracle, cosmic miracle, written in physics and chemistry, but miracle nonetheless. So the next time you hear about a supernova, somewhere in some distant galaxy, don't just think of it as explosion. Think of it as creation, as cosmic gardener, planting seeds that will grow into stars and planets, and maybe life. Think of it as your ancestor, your maker, the source of everything you are, because that's exactly what it is. And somewhere, right now, another star is preparing to give that gift, to scatter its treasures across the cosmos, to seed the future with possibility. The cycle continues, always has, always will, until the last star burns out, the last supernova explodes, and the universe goes dark. But that's trillions of years away. For now, the fireworks continue, the creation continues, the transformation continues, and we're here to witness it, study it, understand it, be grateful for it. Because without supernovae, you wouldn't be here, reading this, breathing, thinking, existing. You owe your existence to stellar explosions, to violent deaths of stars, to the generosity of the cosmos, giving everything away so something new can emerge. That's what really happens when a star goes supernova. It dies so you can live.